Good morning, everyone. I'm Mabuchi of Osaka. I started my job about 20 years ago, and I'm mainly in charge of energy facilities expansion energy terminal, including cryogenic energy utilization facilities. Today, let me explain about cold energy utilization in Osaka gas terminals. Now showing today's contents. At first, I will explain about what is cold energy, and second, examples of cold energy utilization system, and also gases experience of cold energy utilization, and I will show you every facility's detail shown as shown here. At first, what is cold energy? Cold energy is consist of two parts. One is low temperature energy. It's only the temperature difference. And one is pressure energy. About the low temperature energy, origin is energy temperature, minus 160 degrees C. Is very low compared with ambient temperature. So we can use this low temperature energy. Usually, temperature energy is mainly thrown away to seawater using vaporizer. Pressure energy, this is expanding of gas. Pressure energy is mainly consumed by transportation from energy terminal to trunk line to customers. So cold energy has big potential to reduce power consumption and reduction of CO2. Next, I will explain about the examples of cold energy utilization systems. Here, I'm showing the example of the cold energy utilization. One is air separation and liquefaction, producing liquefied nitrogen, oxygen, and argon. And also liquefied nitrogen is used for manufacturing of frozen food and cryogenic crushing and producing high purity methane and etc. Second one is cryogenic power generation, and third one is carbon dioxide liquefaction. And next is the cooling of intake air chilling for gas turbine. This can expand the output of gas turbine. And also cold energy used for chemical plant. Chemical plants need low temperature water or etc. And also cold energy is used for BOG re-condensing, re-liquefaction in energy receiving terminal. We apply with cold energy storage tank. And last one is cold storage warehouse, but this one is not utilized in Osaka gas, but in Japan, there are two cold storage warehouses. This shows cold energy utilization situation in Japan. Almost LNG is used for cryogenic power generation. Total amount is about 1,100 tons per hour. Next one is air separation, and third is BOG liquefaction and carbon dioxide liquefaction, and so on. We also gas occupy these percentage of cold energy utilization in Japan. Next, I will show also gas experiences in cold energy utilization. This shows all the list of cold energy utilization systems in Osaka gas terminal. First one is air separation. This was unfortunately replaced already. This was constructed in 1977. Next one is cryogenic power generation. This is a propane Rankine cycle system. And now on running. This is the world's first cryogenic power generation. Third one is liquefied carbon dioxide and so on. There are 1, 2, 3, 4, 5 cryogenic power generation and 3 air separation unit, and so on. Next, I will explain about each cryogenic energy utilization system. First one is cryogenic power generation. We have 2 types of power generation. One is the Rankine cycle system, and this utilizes low temperature. And second one is direct expansion turbine system. This utilizes pressure energy. We have a total of 5 cryogenic power generation. First one is, as I explained, constructed in 1979, and output is 1.4 megawatt, and the energy usage is about 60 ton per hour. Second one is 6 megawatt, and this is a combination of Rankine cycle and direct expansion system. This explains the system of called cryogenic power generation. Heat medium is, for example, propane or freon. We use both, and the propane is pumped up and pressurized and vaporized by seawater and rotating turbine and reduce pressure, but still vapor phase. And vapor propane is condensed by LNG and pressurized and repeat again. LNG is vaporized here and superheated by seawater, and usually sending out to the high pressure line. But if we have a low pressure send out line, we can utilize pressure energy by rotating turbine, and we can produce more electric power. But it depends on the trunk line situation. This is a plant appearance. You can see here, this is a heat medium vaporizer, and this is a natural gas heater, superheater. And this vessel is LNG vaporizer and propane condenser. And turbine and generator is inside of this house. This system produces 6 megawatt electric power. Next, I will explain about the air separation unit. We have now 2 plants in Senbok terminals. Number 1 was constructed in 1983, and the second one was constructed in 93. Production rate is shown as here, and energy usage is 40 ton per hour and 50 ton per hour. Comparatively, a small quantity of energy usage. This is a comparison with conventional process. This shows the nitrogen liquefaction process of the air separation unit. Nitrogen is compressed and chilled, compressed, chilled, repeat many times, and finally nitrogen is liquefied. We have to compress many times. But if we use energy for cooling the nitrogen, we can omit these many stages and can produce liquefied nitrogen. This system consumes about 50%, half of the electricity compared to the conventional one. Next one is a carbon dioxide liquefaction unit. If you have oil refinery near the energy terminal, oil refinery produces carbon dioxide to reduce the sulfur in the crude oil. So oil refinery can produce carbon dioxide. So we receive the carbon dioxide and cooling, compressed, and distillation column is here, and we can produce liquefied carbon dioxide. And also we have dry ice manufacturing facilities. These carbon dioxide and dry ice is mainly used for food industries, including beer and water and etc. This shows the facilities general view of two plants. Number one plant was constructed in 1980, and the second one was constructed in 2004. And this is the production rate of the liquefied carbon dioxide and dry ice. Energy usage is like this: 5 ton power and 8.5 ton power, very small. Also, this system, this new system, cryogenic energy utilization system, consumes about half of the conventional system. This is a photo of the carbon dioxide liquefaction facilities. This is a tank, a storage tank. And this is a compressor and compressor and cooler. And this is a distillation tower here. Next one is a boil-off gas recondenser with cold energy storage. Usually, a boil-off gas from energy tank is compressed by compressor and sending out to the trunk line. In our system, 4 megapascal is the trunk line pressure, so compressor should be 4 megapascal. But if we mix the boil-off gas to the energy, we can condense the boil-off gas here and pump up again and vaporize this energy. We can reduce the power consumption of the boil-off gas compressor. Typically, 3.5 megawatts compressor is used for the high pressure line, but we can reduce the power consumption 1.5 megawatt. And also, we apply the cold energy storage here. Phase change material is normal pentan. This melting point is about minus 130 degrees C. So, if energy flow rate is big, normal pentan should be solid. if energy flow rate is lower than, for example, 60 ton per hour, melting the normal pentan and gives a low temperature energy to the boil of gas, so we can condense the boil of gas every time. This is the reason we apply the cold energy system for the energy liquefaction. In Europe and the United States, maybe energy send-out rate is very constant. But in Japan, trunk line capacity is very small. So send-out rate fluctuates very much. So usually we utilize the energy cold energy, very small portion of the send-out rate. And all this section is not utilized for the for cold energy utilization system. But if we apply this cold energy storage system, we can utilize this section and use this cold energy here during a low send-out rate. Next one is the intake air chilling system for gas turbine. We have one example in Himeji terminal. Combined cycle gas turbine output is about 5 megawatts, and the efficiency is about 50%. Gas turbine output reduces if ambient temperature is high. For example, ambient temperature is 35 degrees C. Output reduced about to 80% of this value, so 40 megawatt. But if we chill the inlet air, we can recover to this value. This 5 megawatts gas turbine consumes 8 ton per hour fuel, LNG. But if we decrease the temperature from 35 degrees C to 15 degrees C, we have to utilize 27 ton per hour LNG. So only this system cannot balance energy vaporizing of the inlet air cooling and consumption of gas turbine. These are not balanced, so this should be installed in big capacity of the vapor. We can only utilize very small part of the vaporized LNG. Next one is cryogenic utilizing cascade process. Energy terminal, we have such kind of facilities: CO2 liquefaction, butane cooling, and water cooling. And each source, carbon dioxide come from oil refinery, and butane also, and pure water comes from the petrochemical complex, and chill like this and utilize. This system can reduce the energy consumption because of this cascade system. Oh, sorry. Right side is a conventional utilization system. Each plant has each vaporizer, and energy goes through parallel like this. But this system is cascade system, so can utilize the energy more high efficiency. Next one is ethylene refrigerating system. This system is inside of the petrochemical complex. They separate hydrogen, methane, ethylene, and etc. using distillation system, and cold energy is supplied by refrigerator, ethylene compressor, and propylene compressor. Power source is steam. If we apply energy like this, cold energy like this, we can reduce the steam consumption and refrigerator. We can omit these refrigerators and can decrease the steam. Sorry, this system was applied cooperation with a petrochemical company about 5 years ago. Last one is a cold storage warehouse. This system is not utilized in Osaka gas, but I will introduce this system. This shows the object for cold storage. Minus 40 degrees C, minus 50, and minus 60 degrees C. Each temperature level shows appropriate usage. Most lowest temperature is minus 60 degrees C for tuna. And the second one is seaweed and shrimp, etc. In Japan, if we apply minus 40 degrees C, it's better to use electric refrigerator because of a high facility cost of energy utilization. But we can apply for minus 60 degrees C for energy cold energy utilization system, because electric refrigerator is very expensive in this temperature region. So and this is a cold energy warehouse system. Vaporizers here and intermediate heat medium is chilled by energy and pumped up and come to the warehouse and vaporize and return to the condenser. So this system is expensive. So utilization temperature, lower utilization temperature is better for cold energy utilization. Yeah. End of the. Thank you for your kind attention. Thank you.